Hello. Today I will talk about one of our recent work published in Transactions on Machine Learning Research with title Multi-Intention Inverse Q-Learning for Interpretable Behavior Representation. So this talk will be four parts. First one is the introduction, where I will talk about some background and motivation of this work. And then in the second part, I will go into the theory about the algorithm. So how the problem is formulated and how to solve that. And then I will talk about some experiments to compare with the state-of-the-art approaches. And then the lastly is the conclusion. So let's start with some background. So this paper, we aim at characterizing decision-making behavior using inverse reinforcement learning methods, which consists in determining the underlying intrinsic reward function, which means unknown reward function, given expert demonstrations. So inverse RL has been widely applied in engineering, like robotics, autonomous driving, and sometimes even medical care problems. And it appears to be emerging as a valuable tool for constructing mathematical behavior models in behavior neuroscience and cognitive neuroscience research. But a classic inverse RL assumes that the reward function is fixed, underlying the expert whole demonstration. But sometimes it can be extended from the single fixed reward function to multiple and non-stationary reward functions. So based on the consideration that the animal's goals can evolve over time due to like fatigue, satiation, and curiosity, or something like that. And one of the related work that is closest to ours is the dynamical inverse reinforcement learning, published on 2022. So it extends a specific variation of the inverse RL algorithm, which is called the maximum entropy inverse RL, to non-stationary rewards. And that's the state-of-the-art performance in animal behavior prediction. So what it does is that it parameterizes the animal's reward function as a smoothly time-varying linear combination of a small number of spatial reward maps. And the ways is pried with the Gaussian random walk. So it can be written like this. So the R is the reward, while these U's are the small number of reward maps. In here is the K. And then the alphas are the mixing weight, which is prior with the Gaussian random walk, like that. And the smoothness is controlled by the variance of this Gaussian prior. So based on this formulation, you can see that it allows the reward function to vary continuously and smoothly in time. And after this work, there has been demands on inverse reinforcement learning approaches with discrete time varying reward functions, especially after it has been suggested that animals alternate between discrete strategies during decision making. So that's what we're going to do here in this work. So before we go into our work, I will talk a little bit about some preliminaries, which is the inverse Q-learning proposed by Carl et al. At 2020. So they formulate the inverse RL problem as MLE maximization problem. Like they maximize over the expected log likelihood of the demonstrations, and the Xi here is the trajectories within the demonstration space D. And the optimization variable would be R, which is a reward, and this, if we only maximize these, that the problem is ill-posed. So we need to add some constraints. What they do is that they have this Boltzmann policy constraints followed by these Bellman optimality equation. So that guarantees the problem is solvable. So how to solve these? What they do is that, depends on whether the transition probability P or the environment model is known or not. So if it's known, then it is possible to perform a model-based learning. So it's called closed form inverse action value iteration, ERV, and it solves the problem via least squares. And then if the P is unknown, the problem can be solved with stochastic approximation and leads to the inverse Q learning, the model-free inverse Q learning algorithm. So what we do here is that we extend the ERV and HIQL to multiple intention setup based on the following assumptions. So the first assumption is that each expert demonstration is generated according to a Boltzmann optimal policy under one of the reward functions in a set R, which consists of k different reward functions, and each corresponding to one specific intention. And then the probability that one demonstration is generated under reward function R is controlled by a Markov chain with initial state distribution pi and transition matrix lambda. So this decision network can be represented in a graph like this. So these first two columns, the first two rows, are the MDP, at state S and take action A. Then after the transition probability, you go to the next state S. And this column, this row is the transition of the rewards controlled by these transition probability lambda here. So then how to solve this? Solving the inverse reinforcement learning problem on such a decision network with parameters like, as I said, the pi, lambda, and R consists in determining, first of all, a set of reward functions, R1 to Rk, and as well as the reward function index for each demonstration. So we consider the expectation maximization approach. So for convenience, let's introduce this eta, which is the predicted sequence of reward function indices for trajectory psi in D. And then each iteration of the EM process can be written as this. That's also an MLE. The difference is we have to marginalizing out the eta in the objective so that we consider all the combination of the possible predictions. And again, the optimization variable would be the theta plus, which is the theta for the next iteration, and taking the demonstration D and the previous prediction of the parameters as the problem data. Okay, and then can be shown that the problem in the previous page is equivalent to solve a sequence of optimization problems. So the first one is about the pi, and the second one is about lambda, and the last one is about the reward function. Oh, by the way, the last one is actually a sequence of optimization problem because we have to do it for individual eyes. And you may notice the first two is just, can be maximized according to the Gibbs inequality, that when this is equal to the expectation of that, and this one is equivalent to the expectation of that. And for the last one, so, it can be, it can be seen that it has the same structure as the classic inverse RL. The difference is that we have this weight term with respect to the probability that the demonstration at T is under reward I. So to solve this, you can see that we need the probabilities like this one, this one, this one. And luckily, we can use the Baum-Welsh algorithm to calculate these. And after we have that, as I said, we can, the pi and lambda is just equivalent to the expectation of these individual probabilities in the problem. And then for the last one, since the only difference is we need to kind of weight different trajectories according to some probabilities, then what we do is to, first sample a demonstration subset with respect to the probability, and then use the class of inverse Q-learning algorithms to solve the problem under this subset that is corresponding to the specific intentions. So that's the idea. Then I will introduce some experiments. So the first one is synthesized grid world benchmark. The purpose of this experiment is that we would like to show, or we would like to compare, the suitable case for our approach, hierarchical inverse Q-learning, and the state-of-the-art dynamical inverse reinforcement learning. So the environment is formulated as this. So it's a 5x5 grid world with action defined as left, right, up, down, and then state. So, and then it always has a 10% probability to random state, which means that the transition function is stochastic. Okay, and the expert has two policies. The first one is HIQL, which move towards 4, 4 is this. And then abandon means return to the initial point here, 0, 0. And by the way, this is where the expert always starts. Okay, and the whole policy, the mixed policy, considering these two intentions would be the following. So it initializes at 0, 0 with always the HIQL, and then sample action and transition. If they reach some state that has barrier like that, which is this part, and there is a 30% probability of switching to another policy. And besides this, at the eighth step of this episode, there's always 50% probability of switch to the abandoned policy, means that they just give up. And the episode is terminated until the initial point or the destination is reached. So, which means that once they have reached here or here, the episode is terminated. And you can see that these kind of intention dynamics would be more described with the step function instead of smooth function. And it turns out it's the case. So we first compare the performance with the dynamical inverse RL. So for both of the algorithms, we have the one intention set up for baseline, and then we have the two intention model HIRV, and for the dynamical inverse RL, we have varied these hyperparameter which controls the smoothness, which is the variance of the Gaussian prior, from very low to kind of high. And the higher the value means that, in theory, the more step-like that the transition function would be. And first of all, you may notice that, in general, HIRV outperforms the IRL. And it seems that, the different sigmas have little influence on the performance. And then we can have a look at the predict posterior probability of the abandoned intention. And you may notice only EIV can recover the ground truth like that, almost exactly, while the other one just, deviate a little bit from that. And the reason underlying this would be, if you have a look at the policies, the recovery policies. So these first two rows indicates the the state value for the learned policy under the ground truth reward. And the table here indicates the expected value difference, which describes the suboptimality of the learned policy under the true reward. And the lower, the better. The lower means that the learned policy is more aligned with the ground truth. So you can see that the lowest value is here, and from the figure, these two just align almost the same, just almost the same as the ground truth. Well, there's a small value here, and this is quite good, but the other one is not. And in general, you may notice that the dynamic inverse RL just cannot capture the second intention in this setup. So it suggests that although in theory we can change the hyperparameters of the dynamic inverse RL to make it more discrete or less smooth, but in practice it's not so easy. And such scenario, like in this task, would be more, the HERV would be more suitable for such intention transition dynamics. And then we will go into another example, like it's a real world mice navigation benchmark in a maze. It's like that. So there is in total 127 states plotted by the black dots here. And then action space is again the left, right, and reverse and stay. So this is where they start. And there is only one state that is occupied with some water. And the optimal path would be from here to here. So there are two groups of subjects with which is the water restricted mice and water unrestricted mice. So they have different behavior because the unrestricted does not have the engagement to find water. Oh, and by the way, in this environment, we consider the transition function to be deterministic. Okay, and then we can first have a look at the water restricted groups. So if we compare these two, you may notice, so in general, HERV performs better than the DIRL, also shown by the BSE. For the single intention, it's similar, and you may notice also here and here, because it's just both of them reduces to one of them DRL reduced to maximum entropy inverse RL, while the HERV reduces to inverse action value iteration. But when we increase the number of intentions in general, HERV just outperforms the DRL. So and then we can have a look at the policies where the BSE is the lowest. So HERV discovered two intentions. The first one is called tired, because you may notice the policy on that would be from the water or somewhere recent near the water along the way back to the entrance of the maze, which means they just want to get out of it. And the second intention would be thirsty, where they go from the entrance or something near that all the way to the water. And it aligns with our intuition and also shown in the posterior probability of the different intentions. So at the beginning, it's very, the probability of thirsty would be very high and may persist for a while. And then it decreases and the p-tired increases, means that after, for some while, when they acquire enough water, they, just wants to get out of it. So that's it. And it shows that the HERV can produce some, interpretable behavioral representation in this specific task. And then we can have a look at the water unrestricted animals. So in general, the problem would be harder because their behavior in such scenario would be more random, because they don't have the thirsty they can just explore and not searching for the waters. And it's the case because you can see that the log likelihood is in general larger than the water restricted animals, and especially for DRL, increasing the number of intentions just don't have a huge influence on the performance. While for HERV, there's still some increase on that. And again, we can have a look at the policy. It's a little bit different. So the intention one would be exploring, means that like this. It's just tends to go out, or go to the corner of the maze, like really explore the space of that, and go from here to here like this. But for the intention two, it's tired because like this, they just all the way to the entrance from the corners. And for the intention dynamics, plotted here, there's no plateau here because they don't have to get the water; they just explore. And in theory, the probability of exploration can decrease at the first time they entered and something like that. So that's what we observe here. The P exploring decrease directly after they entered, and the P target increases. So the policy under the different groups are different, even if it's in the same environment. Okay, so in general, it shows that for both of the groups of animals, HERV outperforms in predicting their behavior than the IRL, and we both have interpretable behavior, the policy and the intention transition dynamics. So that's the good part of our methods. So lastly, I will introduce a new experiment where we perform model-free learning of the algorithm. It's again a real-world dataset recorded from a dynamic two-armed bandit task performed by a group of mice. So there are two spouts, left and right. So one is rewarded with water and the other is not. And this deterministic reward delivery means that once they leak on the correct side, they will have a 100% probability of getting the reward. And it's called dynamic because there is a block switch, or the reward switch means that the rewarded and unrewarded spout will switch, and it's performance dependent, which says like if they had more than 75% of win in the last 15 trials, then the reward will switch. Okay, to do the modeling, we have to first formulate the MDP. The action space is easy, just the left and right, but the state space is a little bit tricky because it's actually partially observable MDP in this task. So, but to avoid doing so, we perform this kind of formulation, like this of the state. We say the state concept, is a tuple, consists of two parts. The first one is the history extrinsic reward, like the hit and error in the last couple of trials, and that's the action corresponding to these trials. And here the hyperparameter would be the history length, and determines how long we assume that the animals consider to make decisions. And again, as I said, the dynamics of the environment is quite complex, so we assume that's unknown and make use of the model-free version of the hierarchical inverse Q-learning. Okay, so let's have a look at the results. So firstly, the hyperparameter selection about the history length. So we compare the log likelihood on the test dataset, which you can see that the maximum is at the history length of 3. Then we use that as into next step. So we select the number of intentions. And by the way, here we introduced this baseline, which is the forgetting Q learning model. It's widely used in these kind of tasks, the modeling of these kind of tasks. And then you may notice if we introduce more intentions, the log likelihood increases, especially from 1 to 2. And then the basic information criterion suggests that both 2 and 3 intentions are acceptable values. So here we will choose 3 because we would like to have a look at the more detailed policy of the animals. So here it is. So under different intentions 1, 2, and 3, we observe or we define it to be exploitation, disengage, and exploration, because we select 2 matrices, the win stay and lose switch. In this kind of deterministic bandit task, it's like the optimal policy would be 100% win stay and 100% lose switch. So you may notice under the exploitation, the win stay is quite high and lose switch is also above chance level. And for the disengage, the win stay is also above chance level, but the lose switch is just 0.5. Means that if they lose, they prefer to just do some random action selection. So that's corresponding to a so-called passive exploration. Okay, and the last intention is exploration, because you may notice that that's the only one has the more than 0.5 general probability of switch, which corresponding to a very high lose switch and also a very high win switch. Okay, so after we have this policy, we can have a look at the general correct probability under different intentions. So the average for all intentions would be 0.7, and we can see that the probability of correct decreases from the exploitation to exploration. So then the dynamics of the intentions suggest that it aligns with the learning curve. So because after every reward switch, the animals have to readapt to the new reward distribution, and that's why we observe these learning curve, the p-correct here. And at the beginning of reward switch, there's an increase of exploration and disengage, while there's a decrease of the exploitation. But as the trials goes on, the exploitation again may become dominating the 2 of the others. What would be interesting is that we also observed such kind of positive proportional relationship between the average exploitation at the before the block switch and the average exploitation after the block switch or the reward switch. Means that the higher the probability the animals had at the end of one block, then there is a higher chance for them to perform exploration after the reward switch, which is the new block. So this confirms that this exploration is active exploring the environment based on that they have acquired enough information in the previous trials. Okay, then we go into the conclusion. So in this work, we propose the class of HIQL algorithms which outperforms the state-of-the-art on both synthesized and real-world datasets. It also produces interpretable behavior characteristics, and we also use that to characterize typical exploration behavior of rodents during value-based decision making, which is the TRM bandit task. And compared to the state-of-the-art, for characterizing animal behavior, the advantage would be the assumptions about the underlying intention transition dynamics in our methods align better with those observed in real-world behavior experiments